Hi everyone, this is your struggling CS student. Welcome back, and today we'll be solving another LeetCode problem. So let's take a look at today's problem. LeetCode problem 1930, unique length 3, palindromic subsequences. Okay. Given a string S, return a number of unique palindromes of length 3 that are a subsequence of S. Note that even if there are multiple ways to obtain the same subsequence, it is still only counted once. A palindrome is a string that reads the same forwards and backwards. A subsequence of a string is a new string generated from the original string with some of the characters can be null and deleted without changing the relative order of the remaining characters. For example, ACE is a subsequence of ABCDE. Okay. So let's take a look at example 1. S, AABCA, output is 3. There are the three palindromic subsequences of length 3 are ABA, AA, ACA. Okay. Okay. Yeah. Let's take a look at the constraints. Ooh, constraints 10 to the power of 5. Huh. Interesting. So initially, I'm thinking of a dynamic programming approach. At each step, you just take whether you how should I put it? At each stage, you just it's a take or no take thing. It's whether you're currently taking the current character or not taking the current character. And once you reach a character of length 3, then you check whether it is a palindromic subsequence or not. I'm not sure if there are repeated subproblems that we can reuse. Yeah, maybe let's use this as an example, right? So we have B. Initially, we can take B, or we don't take B. So the empty case is it's just the empty case. So empty case I just represent like this. We can take B first, or we don't take B. Okay, let's say we take B, then we take B again. You take B, you take B, you take C. Well, there's nothing here. You know, take, and we take. Do we encounter a subproblem, the same subproblem again here? So we take, then we don't take C, we take B. This is take, this is no take. Oh, right. So the left branch represents when we are taking a character, and the right branch is when we are not taking a character. This is when we are at index. This is when our index is at 0. This is when our index is equals to 1. This is when our index is equals to 2. Right. At this stage, we don't take. Then we take it here. I is equals to 3. Oh, I is equals to 3. We found 1. We can recurse back. Then this represents the case where I is equals to 3, and we don't take it. And now it's here again. It's here again. We do take this. No, we don't take this. Yeah, there's no point. I want to find another B in this case. Don't take, and now we take. Now we take again. So this is BB, and now we take. But technically, this is index 4 and this is index 5. It's not exactly the same subproblem. Not exactly the same subproblem. Wait a second. Oh, okay, I see. It doesn't matter because we are only, how should I put it? They are only counted once. They're counted once. That means every time we reach our length 3, we can backtrack already. We can backtrack, but are there repeated problems? Not sure for this one. I guess it doesn't hurt to try. But we need to keep track of the current length as well. And actually, we need to keep track of the current string. It's a simpler way to do this. I'm actually thinking of a two-pointer algorithm. Thinking a two-pointer algorithm might work. So how's that gonna look like? So let's use this example again. So you have B, B, C, B, A, B, A, right? So what we can do is we can have two pointers initialized like this, and we know that because we only care about palindromic subsequences of length 3, then at this point we put B here and A here. There's no way we can form a valid palindrome in this case. So I guess we can go two pairs, like this, and then we go to the remove from, let's say, the right pointer to the left pointer, right? And now we can replace this with B itself, and realize that actually we can form, within this, we can form any palindrome subsequences. Because once they meet, then we can add this, 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 this. But we can use a set to keep track of palindromic subsequences so that we don't double count them. Okay, we don't double count them. But then if we iterate through like this, that will still be n squared, kinda. Still be n squared, right? Then we can fix it like, let's watch on ahead. Let's iterate through like this, and we count them together. Can we keep track of the number of characters in a range? That sounds a bit tough. We know the characters in a given range. We can add B, C. So in this case, there's 3, right? There's A, B, C here. B, 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 so it's A, B, C, yeah. Okay. We move on like this, we move on like this. Yeah, 2.2 is still hard. 10 power 5, that means we need at least an ON solution or better. What if it's like this? It's like this. So count it like this, and afterwards count. You can count it again. Once it's here, you're done. Then go here, and count like this. And count like this. That worked. Yeah, I'm just going to try that solution where we remove the two-pointer algorithm, remove like this. So once this condition is met, somehow if we can get the count of unique characters within this range, then we can add it to our answer. Can we? Or do we still have to iterate through this? So we go from right to left and then left to right. Right to left and then left to right. That will still be ON in this case, right? Still be ON in this case. I think. Y minus equals 1. Then we set it. S of left is equals to S of right. Then we can somehow break it. I in range from left plus 1 to right. Answer dot add S of left. Now the string will be, let's say S is like this. Oh, I can't do that. Dot join S of left, S of I, and S of right. Let's just print answer first and take a look. Left. Yes. Maybe. It's hard to say though. It's hard to say. So likewise here, go the other way around. I'm not confident that this will pass at all. Oh my days. Let's see. God dang it. Okay. That's the answer. Left plus 1 to right. There are 9 of them here. There are 9 of them here. Oh, because we only fixed the 2 endpoints. It could be the case where it's like C here, and then you have C in the middle, right? You see, that's the one that we're missing. Yeah. So how do we solve for this case? We only fixed the two endpoints. Do we keep going? Do we keep going? But how though? How though? Let's see. So this should also be wrong. Basically, we have had the case where there's also length-3 inside. Okay. So it's like this. So, wait a second. Wait a second. I'm thinking of another way where it's essentially also a two-pointed algorithm. But in this case, you only keep track of the left and right boundaries. Which means to say what? Which means to say you want a pair of characters that are always unique at the boundaries. What I mean to say is that if let's say you ever see two that are the same, like for each unique character, you want to find the rightmost character that's also the same. So let's say you will find B and B, you mark these boundaries here, you have C and C here, you mark these boundaries, then you have, but how do you mark this and this though? How do you mark this and this? The nearest A. Oh, we can search it, right? So you can use a dictionary to group them together, and then you can search it. Then you can search it. English characters. I think that might work. I think that might work. So essentially, you probably still need an answer set. In this case, for each character in C, for each character in S, you keep track of their positions. I see the enumerators. Default index of list. So dc.n bring d. Let's have a look. Right, okay. So now you only care about the ending positions 0 to 7. 0 to 7 means what? That means any characters from 0 to 6, you can form it. Technically, can you form it with every other character? I mean, as long as they are a character within a range of 0 to 6, then you can form it with this. But how do we count it though? How do we count it? Let's say you have a case where it's like this. So 0 to 6. In this case, C, 2 to 5. Just thinking if it's like the easy case would be you just iterate through, right? So 0 to 6, and then iterate through 2 to 5, and then you just keep checking like this. But I wonder if there's a smarter way of doing this. Wait a second. Oh, I don't know the characters there. Characters from 2 to index 2 to index 5. Index 2 to index 5. Yeah. Hmm. Fix them at this point. You check. Technically, you could have a 24n answer, which is the brute force part. It's definitely possible. Okay, so let's think about what's the worst case. The worst case is if you have like all unique characters A, B, C, D, all the way until like the end, and then it's like to Z, right? And then you have Z all the way again to Z, Y, X, Y, Z, X, and then it's like you have D, C, B, A, right? So every time you go from here to here, you have to scan it through like this, and then the next iteration would be from B onwards. So from B onwards, then you have to scan like this, and then from C onwards, you have to scan like this, right? The time complexity would be what? 24n. 24n. Technically, this is a constant, and well, big big O of 24n is actually still big O of n. I mean, you can try that. No harm trying. See if it works, and then, well, that's all I have going on for me right now. So for each character and its list of values or its indices in d dot keys or d dot values, right? D dot items, right? And the first last is equals to indices of 0 and indices of -1. And actually, if the length of indices is less than equals to 1, we can continue, which means there's only a single character at this point. So now with the first and last, we can just iterate through for I in range from first plus 1 to last up to 1 not including last. Then I can say answer.append dot add dot join of s of left, s of left, s of y, and s of right. Left is not defined. Oh, I'll do this left, right. Huh? Oh, I see. Is this really the right way to solve this? I'm gonna submit it. 24n. Should be good, right? Okay, it's accepted. So I'm happy about that, but I feel like there's probably like a smarter way to do this. But let's take a look at what the tutorial has to say. Count letters in between, which is kind of like the approach that I had. Yeah. What did they say? Okay, so the left index, the right index, and then you have a set. So you just edit Python one-liner. I'm not gonna read that. Yeah. Oh, sorry, it's not 24n, 26n. Because there are 26 characters in the alphabet. Okay, so this is the approach that I thought of. Pre-compute first and last indices. By pre-computing, it does add a large constant. We will spend on once and retrieve ij for every. Okay, let's see how they do that. So you map it like this. The first and last. Wait, it's still the same. Giving us time complexity of 26n. Oh, that is. This is not. Wait, really? Yeah, I mean, come on, it's all alphabets, which is technically all constant space, but okay, fine, you can say that. So basically, instead of tracking like all the palindromic subsequences. Oh, actually, wait. Actually, maybe we don't need to track. Maybe we can just have a counter, and then, oh no, no, it doesn't work. No, it doesn't work at all. Yeah, because we will double count and stuff. Yeah. So we need to keep track of the um the set of palindromic subsequences that we've already seen. But yeah, took me quite long for this one, but I guess I'm still happy that I managed to solve a 9-day trick. So yeah, thanks for watching, guys. Have a great one.